All right, so today we are having Gwen May and Justin Siebens. Gwen May is currently serving as the Assistant Geometrics Engineer in the Minnesota Department of Transportation Central Office, where she's worked since 2017. Her primary responsibilities include oversight of design, policy, and guidance, training, geometric layout review and approval, project management and research. In the 8 years prior to her current role, she gained experience in environmental stewardship, state aid, hydraulics, roadway design, and construction. Gwen earned a Bachelor of Science degree in civil engineering with a transportation emphasis from the University of Minnesota. In her spare time, she enjoys spending time with her family, traveling, and exploring new cuisines. And Justin Siebens is a senior project manager at SRF Consulting, where he's worked for the past 8 years. Justin has 12 years of industry experience focusing on transportation mobility. His work primarily includes medium to large scale projects consisting of corridor studies, freeway modeling, noise analysis, and air quality work. Justin is also involved in the emerging technology field with an emphasis on video-based data collection and leveraging AI to analyze intersection operations, near misses, and multimodal interactions with vehicular traffic. Justin has a Bachelor of Arts degree in physics from Carthage College and a Master of Sciences degree from civil engineering at the University of Wisconsin-Madison. Outside of work, Justin splits his time being an Irish dance dad for his daughter and a baseball coach for his son. So give it up for Justin, or whoever's starting. Gwen will be starting today.
Thank you for the kind introduction, Olivia. Can you hear me? Okay. Good afternoon, everyone. I'm really excited to be here with Justin to share with you our recently completed road roundabout study. As you have all know, roundabout has been proven to provide significant safety benefits for all roadway users when they are implemented at the proper locations and when they are designed appropriately. Despite the benefits, the construction cost of roundabout has been rising over the years, both locally and nationally. MnDOT has consistently sought opportunities to reduce costs, minimize costs, while maintaining the functionality of its design and its elements. A couple years ago, our local partners has raised concern over the practicality of incorporating separated pedestrian and bicycle facilities at roundabouts in remote areas, simply due to the challenge with winter maintenance and the lack of pedestrian usage. As a result, MnDOT, in collaboration with our local partners and acknowledging the variation of design practices within the industry, we constructed a few roundabouts without external curb and without pedestrian facility accommodations. Because these designs are new to us, that's why we initiated this study. And I'm here today to share with you our findings. The agenda for today's presentation include project overview, the definition of urban and rural roundabouts for the purpose of this study. And something really interesting is that we use the latest technology. We actually use AI to analyze the videos that we collected. And we also surveyed the districts who constructed these rural roundabouts and asked for their reasoning and their perspective of considering and constructing this type of roundabouts. And of course, we included the 4 roundabouts that we will be studying. Like we have 2 urban roundabouts, which served it as the control, and then 2 rural roundabouts. Those are our experimental locations. And finally, we will go through design considerations and key takeaways. And for project overview, this project, it was completed under the partnership with MnDOT GDSU, which is where I work. And I'm also the project manager of this project. SRF, which is Justin, who is SRF's project manager. And also University of North Carolina, Charlotte, they provided the AI analysis. And the goal of this project is to understand driver behavior in the rural and urban roundabout designs. And we also would like to determine the R1, R2, and R3 speeds and identify any off-tracking behaviors using vehicle envelopes and heat maps. Also, we will look at driver yielding behaviors to other vehicles as well as pedestrians. And also, we will compare driver gap acceptance. Here are our project, our roundabout locations. We have 2 urban roundabout and 2 rural roundabout. The urban roundabout, the Trung Highway 59 and Kasa 3 urban roundabout, and the Trung Highway 75 and Kasa 21 roundabout, rural roundabout, is located at northwest Minnesota. And then the 2 Trung Highway 13 roundabout, which one is urban, one is rural, is located at southeast Minnesota. One thing to note, the urban roundabout are selected because they have similar geometry and close similar geometry as well as similar AADTs, and they are close to the rural roundabouts. And as you can see from this image, right, the image on the right is an image of how we set up cameras. Cameras are set up at all four quadrants of the roundabouts, and those perpendicular lines represent the view angle of the cameras. And on the image on the left shows how the camera was actually mounted to the light pole nearby. And videos were collected for 5 to 6 days for 3 locations, only 1 location for 2 days. That was the Trung Highway 59 and Kasa 3 roundabout location due to issues with equipment. All locations included a 24-hour recording, which our goal is to capture driver behavior at night time. Here are our urban roundabouts for this study. The Trung Highway 13 and Kasa 8 urban roundabout, as you can see, it has separated non-motorized facilities that is actually separated by a grass boulevard. And it also have full pedestrian accommodation, including ped ramps and crosswalk striped, and then also pedestrian refuge at the Spitter Island. On the Trung Highway 59 and Kasa 3 location, the pedestrian accommodation is slightly different. It's actually immediately back of curb. For the rural roundabouts, the Trung Highway 13 and Kasa 28 roundabout, as you can see from the picture, it does not have external curb. And it also does not have separated pedestrian accommodations. However, there is a cut through that you can see right here. Pedestrians are expected to use the striped shoulder to get through, to navigate through these roundabouts. On the Trung Highway 75 and Kasa 21 roundabout, this roundabout has some countermeasures implemented, which include, as you can see, the roadway was paved with concrete, and the shoulder is actually paved with bituminous. So some pavement contrast was incorporated into this roundabout, as well as you can see the edge line rumbles that is also incorporated to discourage lane departure. And with that, I'm going to turn over to Justin.
Justin, if anybody says they can't hear me online, I'm going to clip this. I have 2 hands here. So thanks, Gwen. Give an overview here of the AI program itself. Can't take any credit for this. This was all UNC Charlotte. So out of their electrical engineering group, they've developed this model. One of the reasons we went with them, their model specifically uses and has been trained on lower resolution cameras. So a lot of the safety studies that folks are doing, one of the biggest things we hear from the vendor side is we need high definition video, right? We need HD, we need HD. And given the location of the roundabouts, we were kind of concerned with battery life, being able to collect this from a high definition standpoint without a power source out there, without a trailer mounted camera. And so in talking with UNC Charlotte, they said, hey, we've got this AI system that we can do on lower resolution video. Let's try it out. So that's the path we took. This is really the guts behind the scenes. But ultimately on the right side of the screen here is the single frame piece. So this is, it's identifying the vehicle, whether it's a car, it's a bus, it's a truck, if it's a sign or something like that, we can actually remove those. So that's that filtering piece that's kind of the middle of the screen there. And then ultimately what happens is we stack all these frames on top of each other, and you can actually track the vehicles through the frame, and then you can do the anomaly detection there at the end. So that is my non-scientific description of what this is doing in the background, but a nice picture here in terms of kind of what's going on. This is a screenshot of the system operating. In this case, you've got the SUV pulling a small boat, clearly leveraging the striped shoulder to take that corner, probably taking a right turn in this case, given the speed that they're able to progress or track through that roundabout. And then you'll notice the sign in the middle of the roundabout, the directional sign there. That's one of those object detection pieces. So the system is going to pick up on it, but it will remove it, right? So we don't have that anomaly in the picture frame. But this is just kind of an idea. It's probably hard for folks online to see, but for folks in the room here, you can see that yellow tracking. That's the center of the mass of the vehicle. So while this person at this point is kind of over here now, when they were back here, they were kind of tracking right on the edge of the pavement there. As Gwen mentioned, we did a survey of the districts. So District 1, 2, and 7 have all implemented a rural roundabout design in the districts. And so we wanted to ask them, how are these working? You know, why'd you do it? Why'd you go that route? What were some of your considerations from a design standpoint? Was cost a factor? Were PEDs a factor? And so this is the 8 questions that we asked. Not going to read all of them, but the answers can really be put in 4 buckets. So we've got the design considerations and location piece. So to Gwen, what Gwen mentioned earlier, the context was key, right? Why do you do this? We don't necessarily, from a maintenance perspective, want to have full PED accommodations out there during snowstorms. They saw it as a potential liability, being able to get out there in time to clear it. The functionality piece, in general, they were operating as expected, but not a surprise. Folks were, at least visually, they felt we're driving through them faster at a higher speed than a traditional urban roundabout with that outside curb and gutter. From a maintenance perspective, the rural roundabouts did see quite a bit more off tracking, and you'll see that in some of the videos, some of the heat maps that we're going to show later. You can actually see the rutting in those pictures. Cost was a factor. We had one district that noted a $300,000 savings on the cost of the roundabout, but it wasn't the key factor, right? It was just one of many factors that they took into consideration there. So as Glenn mentioned, we had 4 locations. So we have our two urban locations. This was the first one, Trunk Highway 13 and CASA 8, which was in the southeast region of the southeast portion of the state. This is the one that had the trail facilities with the separated grass median there. The values you're seeing on the screen, so these are our R1, R2, and R3 speeds that we were able to gather from each approach, and its average speed 85th and then the 95th percentile. Some of them do have a star next to them, just due to the lower resolution camera and the width of these roundabouts. You can imagine when you're looking at that, we're just looking at the screen here, when you're looking at that exit speed way back here at the crosswalk, you're about 200 feet away, give or take. And while with an HD camera and some of the technology that's out there, we might be able to capture a speed there. How accurate it's going to be is pretty, it's going to be tough. I see Joe's. I can do that. For those who aren't, so R1 is actually right before the crosswalk here on that entry speed. And then R2 is kind of right in this general area here from a circulating perspective. And then R3 would actually be on the back side of that far crosswalk. So that's part of the reason why that R3 speed is so hard to capture from a video perspective, at least in this field of view. And we wanted to make sure that all the speeds were for each individual vehicle that traversed through here. So yes, you could kind of stitch videos together and you could get all the R1 speeds here, all the R2 speeds there and then the R3 speeds from a different camera, but it would be hard without, you know, true object detection, license plate, color of vehicle, type of vehicle, to then match those back up. So we did estimate the R3 speeds in a few locations. In general, these are exactly what we would expect. You shoot for that 20 to 25 mile an hour R1 entry speed on an average speed perspective, and we're kind of right in that realm. And then looking for that drop in the R2 speeds from a circulating perspective, and then that speeding back up as they exit the roundabout. These are the heat maps that were produced as well. So in addition to speeds, we looked at trajectory lines and where the vehicles were spending the most amount of their time. For folks in the room, you might be able to see the orange lines here that kind of denote the outside and inside of the vehicle tracks. These were based on where that occupancy rating or occupancy number changed kind of from that 50% and under. So from a color standpoint, when we start to shift from orange to yellow, on there is roughly where we drew that line. The colors on here, blue, purple, that's an area that wasn't occupied very often. And then as you get closer to one or closer to the red side, that's an occupancy closer to 100%. So, and that's when there's actually a vehicle there. So when we track a vehicle that goes through, that's how that density was calculated. In this location, we had about 10 to 20% of the vehicles actually tracked outside of the traveled lane into the gutter. So even though this had curb and gutter, vehicles were still using it to traverse through the roundabout. And just for reference point, the HCADT, so the heavy vehicle ADT out here was about 3 to 6%. So it's not just trucks that were doing this. We had passenger cars as well that were doing this. Similar situation for the other urban roundabout in the northwest portion of the state. As Gwen mentioned, we did have a camera issue out here for this one, so we didn't get as much data, and unfortunately we lost the ability to get good eastbound information at this location as well. But from a number standpoint for R1, R2, pretty consistent from what we saw at our other location. And then similar from a heat map standpoint too. So for this one, a lot less in terms of people kind of driving outside of that designated lane, out onto the gutter. But we do have a little bit higher heavy vehicle percentage. So apparently folks in Northwest Minnesota stay in the lanes a little bit better than folks in Southeast. But I will note that we did have one of the trajectory lines that actually drove over the curb or went over the curb. So we did have one vehicle that traversed over the curb at this location. Now the rural roundabouts. So this was the other Trunk Highway 13 location down in Southeast Minnesota. This location had just a striped shoulder. This is the one that did not have the color contrasted pavement with the bit on the outside. And you'll notice in general, the R1, R2 speeds are higher across the board. Not quite if you went, approach by approach, they might vary a little bit, but in general, they are higher for this location. And I mentioned earlier, for those in the room, probably might be able to see it, maybe not, the rutting as well in that camera view. So some significant tracking issues here at this location. And our heat maps told us the same story. So we had over 50% of the vehicles actually traversed on the striped shoulder to go through the roundabout, and only 7 or 8% heavy vehicle. So quite a few passenger cars that are doing the same thing. This is the example too with the boat from earlier. So quite a few folks who are doing it. And we had 10% of the vehicles were actually driving right up to the edge of the pavement. So they are cutting it as far over as they can to get through the roundabout. And then I mentioned the rutting as well on this one. Our other locations, so Trunk Highway 75 and 21 up in Northwest Minnesota. This had the color contrasted pavement, as Gwen mentioned, and the rumble strips right on the back side of the edge line there. In this location, R1, R2 speeds were about the same as the urban roundabouts, and were slightly less than our other rural roundabout. So in general, people were kind of slowing down a little bit more. The biggest difference is really in that R2 speed column is where we saw the most difference between the two rule designs. And the heat maps tell the same story. So less than 10% of vehicles actually off track outside of that designated lane. So on the striped shoulder outside of the rumble strip. And we had 28% heavy trucks here. So not all trucks are tracking off either. So this really kind of helped keep people in the lane where we want them to be, provided that kind of line of sight for folks. Where am I supposed to be? Where I'm not supposed to be? And at the time that we did this, there was no apparent rutting outside of the pavement either. So another nice piece there for this one. But you can see the lines are a little harder to see on this one because the density is so high there in the traveled lane, but everybody's kind of hugging that inside island and then, you know, going to the outside as they traverse through, kind of traditionally what we would expect to see. And with that, I'm going to turn it back over to Gwen.
All right. These tables summarize. Is it on? Okay. These tables summarize the data that Justin have gone over. So it summarizes all 4 roundabouts, all 4 the R1 speeds, and it summarized the average speed, the 85th percentile, and the 95th percentile. As you can see, when you compare the R1 average speed between the Chang Highway 13, CSA A, and Chang Highway 13 and CSA 28, you can see that the rural roundabout has slightly higher R1 speed when compared to the urban roundabout. However, when you compare the Chang Highway 59 and Chang Highway 75 roundabout, the opposite happened. So the urban one actually have higher average R1 speed than the rural design. Because of this, we kind of couldn't make a conclusive decision on whether or not drivers are driving faster on the road design when compared to the urban design. But however, when you compare the R1 average speed for both rural roundabout design, you can see that the rural roundabout at Chang Highway 75 that has the countermeasures like edge line rumbles and color pavement contrast, it has lower R1 speeds. That suggests that those countermeasures are effective in reducing R1 speeds. And what we have found from the 85th and the 95th percentile speed, those are higher, and which suggests speeders are traveling faster through the rural roundabouts. Oh, one thing I forgot to mention is that the average speeds on all urban and both urban and rural roundabouts, they are within the range of anticipated signaling roundabout entry speeds. And this table summarizes the percentage of vehicle off tracking for all 4 roundabouts. As you can see, on urban roundabouts, drivers are driving the roundabout as intended, with roughly 10 to 25% of vehicle driving over the gutter. It actually depending on which urban roundabout that you're looking at. If you are looking at the Chang Highway 13 and CSA A rural roundabouts, it has 10 to 25% of tracking over the gutter, which suggests that both the heavy vehicles and the passenger vehicles are using those gutter space when traversing through the roundabouts. But when you're taking a look at the Chang Highway 59 urban roundabouts, it has actually less than 10%. That kind of suggests to us maybe that is just only the heavy vehicles are using the gutter space. When you compare the rural roundabout of tracking, the difference between the 2 rural roundabouts are drastically different. The one with countermeasures such as pavement contrast and rumble strips, it only shows less than 10% of lane departure behavior. And the one without those countermeasures shows a high percentage of lane departure, 50 to 70%. This table indicated that the countermeasures are effective in preventing lane departures. And this table summarizes all the gap acceptance for both AM and PM for both roundabouts. The gap acceptance for all roundabout type are within the 4 to 6 seconds range. It's actually within the anticipated range for roundabouts. And what we have found is that gap acceptance are actually pretty consistent between rural and urban roundabouts. And so the key takeaways for this project, what we have found is that when we are considering these road type of roundabout designs, we should incorporate edge-right rumbles as well as pavement contrast and also with shoulder striping too. Lessons learned that the lessons that we have learned is that we should have used higher quality videos and maybe set an additional camera to capture the R3 speeds better. And maybe we should use drones or set up trailers to set the cameras higher so we have a better view of all the driving happening. And also, we should definitely select a location with higher pedestrian usage so that we can better capture those driver yielding behavior to pedestrians. But since we did not capture any pedestrians at any one of these roundabouts. And I think that concludes our presentation. Any questions?